right, hi guys. So this is going to be a video that kind of walks through how to do the problems that you were working on in class. There are several of them. I don't know if I'll make a video that covers all 8 tonight, but I will try to make at least the first 4, just so that you know if you are doing them right or not. If you are still struggling after watching this, please don't fret. I am hoping to be back by the end of the week, but I do want you to kind of go back through and see, what did you do differently than what I did? Why did I label things differently than you? What am I doing differently as far as the steps? So make sure you're actually following the steps that we were given. And just to kind of remind everybody, we have the problem solving steps on the left. Remember that this was all from 2.6 in the reading, and then we have the kinematic equations, which is all covered in section 2.5. And this is, I'm doing this where I posted or where I created the problem set. So if you ever want to go back and just look at these specific problem answers, which I will go through and I will set them all up. I'm just going to film the first 4, but you can always go into our content library. It should be on the left side of your screen over in OneNote. But if you go into the content library and then you go to homework and you go to the 2.5 problem set, you'll be able to access all of the work that I've done. So you can double check what you've been doing. All right. Okay, so let's go ahead and get started. So number 1 says a bullet in a gun is accelerated from a firing chamber at the end of its barrel. So I'm going to draw a gun. Please don't draw guns on often. My guns are not pretty. At an average rate of 6.2 times 10 to the 5th meters per second squared. Meters per second squared is, of course, the unit for acceleration, so we know that that's an acceleration. And we were also given a time. But we know that there is a situation happening where something is leaving this object, and we're trying to figure out how fast this thing is moving after it's done moving. So there's my sketch, and that was, of course, problem step 1. Step 2 is to list the unknowns and knowns of the problem. So I am, of course, going to copy down all the ones I know. And then I'm going to start filling in what I know. So I do not know an X final, but I know that if it starts in this gun, that I can define its initial position as 0. It also says what is the muzzle velocity, its final velocity. If it's starting in this object that isn't moving initially, then its initial velocity is going to be 0. Looks like this is the thing I'm wanting. And that's part of course, problem step 3. A was given as 6.20 meters, times 10 to the 5th. Per second squared. Time is given as, so just to kind of make sure I understand, it says what is its muzzle velocity. That means what is its velocity basically as it's inside this gun, so from its starting position to right as it leaves the opening. So this diagram is actually wrong because it does say what is its muzzle velocity, and it makes sense because it's a really small time. All right, so now I'm going to go back up and I'm going to look for something that solves for V, given all of the things I have. It looks like I could probably use equation 3 for this because I have V, or I'm solving for V. I have V naught, I have A, and I have T. So I'm going to use equation 3. This is, of course, problem step 4, which is to pick an equation. Problem step 5 is going to be to actually solve the equation. So I'm going to plug in the fact that I don't know V. I'm going to plug in my initial velocity of 0, and then I'm going to do the 6.20 times 10 to the 5th meters per second squared times the time, which is 8.10 times 10 to the negative 4th. And when I do that, since V is a velocity, it's going to have units of meters per second. I'm going to go ahead and type that in my calculator. And I get from my calculator a velocity of 502.2 meters per second. That sounds really fast, but that also makes sense if it's a bullet coming out of a gun. So I'm going to go with that's cool. All right, so we're going to move on. All right, next up at number 2, says, while entering a freeway, a car accelerates from rest at a rate of 2.4 meters per second squared for 12 seconds. Draw a sketch of the situation is step 1. So the car entering a freeway. At first, he's not moving, is what it says, and then he's kind of going up a ramp. He has an acceleration that's in the same direction as his velocity. We're going to list, so this is all, of course, step 1. 2 and 3 are to identify knowns and what my goal is. Always start by writing out all the variables and then trying to go through and identifying them. It says to go, so his acceleration is 2.40 meters per second squared. Since it's in the same direction of the motion, acceleration is, of course, positive. And it says for time, 12 seconds. It also says that the initials, so it says that we start from rest, which gives us information about initial speed being 0 meters per second. Now it does say list the knowns and unknowns, but you wouldn't know what the knowns and unknowns were until you got to part C. So the first one asks, how far does the car travel in those 12 seconds? Please, I hope by now we understand that initial position can be set to 0 if the thing starts wherever we want it to start. Remember that we define position as a starting point, and the difference between the starting point and the ending point is its displacement. So we know that the initial position can also be set to 0. Since it says how far does it travel, I would say we're probably going to want to solve for x in part C. It looks like in part D, you're going to have to solve the whole thing again. But the setup will be the same as far as the initial stuff for both part C and D. So for part C, we want to solve for final x, and in part D, it looks like we're going to do the whole thing again and solve for v. Now, once we know x, we can fill that in our table, and we can go back and we can use that information to help us solve for v as well. These two situations are connected, so it's okay to have overlap as far as variables are concerned. But for now, let's find a value that will let us solve for x given v naught, a, and t. Back up to my equations. I've got v naught, a, and t, so I could probably solve for v, but I need x first. So I'm going to look at here and see that I have all of these different variables, and I think I'm going to use this one to solve for x. Could I theoretically solve for v first and then use this one to solve for x? Absolutely. Could I theoretically solve for final v and then also then use this one? Of course you could. Just recognize you cannot use equation 1 because we do not know the average velocity. We can only find out average velocity in equation 2 if we have both the initial and the final velocities. All right, so I'm going to use, what did I say, equation? Oops. I'm going to use equation 4 first. And then I'm probably going to use equation 3 over here once I'm done with equation 4. All right. Want to make sure that we understand that those are not. This is step 4. Using equation 4. How not confusing is that? All right, so equation 4 is x equals x naught plus v naught t plus 1/2 at squared. Equation 3 is v equals v naught plus at. Pretty sure. Yeah. Okay, so now part 5 is to plug and chug. So I'm going to plug and chug over here to solve for x. Looks like x is going to equal this. Yeah, there's a lot of zeros on the board, so this one's going to go away, this one's going to go away. Looks like x is going to equal 1/2 times 2.4 times 12 squared. And when I plug that in, I get 172.8 meters. And again, once I know it, I can put it over in my table. So I'm going to go ahead and do that. And then I'm going to go and I'm going to solve equation 4. So I guess last step is, does it make sense? Based on the speed it was moving, the acceleration it was moving, that it only covered about 200 meters makes sense to me. Okay. All right, next thing is going to be to solve the second part of the problem. Sorry, I'm just going to move this real quick. Next thing is to solve part D using a different equation. So now we have V equals V naught plus AT. I'm going to plug my numbers in. When I do that, I get a final velocity of 28.8 meters per second. Again, let's ask ourselves, does this make sense? I would say yes, because it's gaining 2.4 meters per second to its speed for every second it's in motion, and it does that for 12 total seconds. So that answer does make sense to me. Moving on. I'm going to do one more, and then I'm going to solve the rest, and you guys can come back to this sheet and you can look at your answers in the morning. All right. The next one says blood is accelerated from rest to 30 centimeters per second in a distance of 1.8 centimeters by the left ventricle of the heart. Make a sketch of this situation. Okay. Okay, so let's pretend like we're in a ventricle of the heart. Doot, doot. Don't come at me about this. All right, so it says in a distance of 1.8 centimeters, blood is accelerated from rest, so 0, to 30 centimeters per second, which is going to be our V final, at a certain distance. The question that we're going to answer is actually part C. So it says, how long does this acceleration take? So it looks like we're going to be looking for time. All right, so I'm going to start, and I'm sorry, my diagrams are terrible, but I drew a diagram. I'm going to start by listing my variables, just like we always do. Remember that there is always some stuff we can garner that may not be given. Like, for instance, if it starts from rest, we can automatically assume that initial velocity is 0 and initial position is also 0. We're told it's going to go 1.80 centimeters. Should you convert these numbers? Sure. Do you have to in this particular case? No, because you have the both of your units are the same. So if this one was given in meters, so if the 1.8 centimeters was in meters, and then the final velocity was in centimeters, then you would want to convert one or the other. But for now, since they're both in the same unit, we're good. We're just going to leave them alone. We're just going to have to make sure we report final numbers according to those specific units. All right, so blood is accelerated from rest. We don't know the acceleration. One of the questions that we are asked is, what is the time? That's the variable that we need to solve for. And then we want to look. So number 4 is to pick an equation. All right, so in picking an equation, we're going to go up and we're going to look. We have both x's, both v's, and we want t. Now, looking at all of these different equations, it took me a second to realize this, but we don't have one that's going to directly benefit us. So instead, we're actually going to have to solve for acceleration first, and then use that value and plug it in to a different equation to find time. So what I'm going to do is I'm going to use equation 5, then I'm going to go ahead and I'm going to use equation 3. There is one other approach, and that's to calculate V average by taking the final velocity plus the initial velocity, dividing it by 2, and then plugging in those numbers into equation 1. So there's 2 approaches to this problem, and you're going to find that there are 2 approaches to a lot of problems. No matter what approach you pick, you should get the same answers. So if you do it 2 different ways, that's fine. Just make sure that, like, if I do it one way, you get the same answer as I do, no matter which way you pick. So I'm going to do 5, then 3 for my equation approach, but you could, the only other one I saw, you could do 2, then 1. Doesn't mean there's only one other approach, it just means that's the only other one I spotted. Okay, so equation 5 is the v squared equals v naught squared plus 2a x minus x naught. Okay, and equation 3, which is going to be my second one, once I have the value for a, is going to be v equals v naught plus a t to solve for t. Okay, so for this first one, I have the 30 centimeters squared is going to equal, remember this one was 0. This one is 1.8 minus 0. Okay, so I'm going to go ahead and I'm going to solve for that. So this becomes this. I'm going to divide by 3.6. I'm going to get that a equals 250, and this would be in centimeters per second squared. Remember that we're not changing our units. One of the things you can do as you solve problems is you can actually plug them in to the table as well. So I'm going to go ahead and I'm going to enter that into my table just to keep track of all the information. Then in step 3, I'm going to go ahead and I'm going to solve for using that velocity, that acceleration. I'm going to solve for that t. When I do that, I'm going to get 30 over 250, which equals t. So t equals 0.12 seconds. All right. Our very last question says, does it make sense? First off, it's blood in the heart. It's a very, very short distance. Does it make sense that it would move quickly? Yes. Does it make sense that it would take very little time to only move about 2 centimeters in your heart? Absolutely. So this absolutely makes sense. If this was anything higher than a second, I'd say that's probably not true, because think about how long it takes your heart to beat, just a single beat. And that's what they're talking about, essentially. Okay, so that's going to be the end of the video. If you want to come back to this page and check your answers for the last 3 or 4 that you're going to do, those will be available to you in the morning. All right, have a great night.